Hi, everyone. Thank you all for coming. This is the preliminary design review for the Spaceport America Cup project team of the Buckeye Space Launch Initiative. So thank you all for coming. Appreciate you taking the time out of your days to spend some time with us and take a look at the work we've done so far. Okay. All well? All right, sorry about that. We were trying to get the lights to work so you guys could see a little bit better, but I think this might be the best we can do. All of you that the email invite should have gone out to should have gotten another one yesterday with the slides in it. So if you'd like to open that up and follow along as we go, or you can just listen to us and follow along here. So we'll go ahead and get on started. So the purpose of the Spaceport America Cup team is to compete in the 2023 Spaceport America Cup, which is hosted by the Experimental Sounding Rocketry Association, otherwise known as ESRA. This year, this competition will be taking place between June 19th and 24th over the summer out in New Mexico. So what we want to do is develop and present BSLI's most refined and technically advanced high-powered rocket. We want to do the best work we can do and hopefully do good competition. And obviously, we want to meet and engage with other members of their schools and just people in the intercollegiate and amateur rocketry community. That's what we're going to try and do. So the goals for this project, like I said, we want to do good at the competition. So we want to have a nominal flight in the 30K SRAD, student research and design category for 30,000 feet at the Cup. Obviously, like always, we're going to prioritize the health and safety in every meeting, make sure everything that we're doing is safe and everyone's being careful. And like that. Obviously, we have to conform to ESRA's rules on design, which is basically just following the requirements that they lay out for us in our rocket and motors and things like that. A little different, what we want to try and do is present a majority SRAD final vehicle design rather than just our motor, which is specified by the rules. We try and make most of our design, student research and design, just to have a better experience for everyone and all that. We want to supplement academics with hands-on engineering experience, just to get people out of the classroom, give people a little bit more than they get just coming to Ohio State, and we want to do that to maintain a thriving rocketry community here. So what we've been looking at so far this year, in this past competition, we placed 32nd out of 93 overall, and 4th in the 30K SRAD category at the 2022 Cup. So obviously we want to do better than that. 4th in our category is not the best. So to do that, we want to try and understand the problems that occurred at this most recent competition. Most notably, issues that we've had with recovery in our propulsion system, and hopefully those can get us to a better place. To do that, we want to try and place a stronger focus on analysis and simulation to try and understand the problems that might happen and have a good understanding of what we're trying to make. Along with issues with our propulsion system, we want to try and make everything lightweight to hopefully have a better chance of reaching our altitude goal. So we're trying to bring the weight down. Over the past years, it's kind of jumped higher, so we're going to try and bring that down a little bit. And as always, we want to advance the capabilities of our current sub-teams to hopefully present some better work. And now I'm going to pass it over to my deputy project manager, Sarah Malaska, and she's going to talk about our team.
All right, hello everyone. Like Zach said, my name is Sarah Malaska, and I am the deputy project manager for the Spaceport project team. So just for a little team breakdown for everyone who's not aware, our team consists of Zach, our project manager, myself, the deputy project manager, and then our 6 leads: structures, payload, propulsion, avionics, aerodynamics, and recovery. So the way that this PDR will work is that each sub-team will present first their sub-team purpose, second their system requirements, then their process to design, their system overview, risks and mitigation methods, their schedule for the year, Following all of this, we'll open it for questions. I will leave 5 minutes for questions after each presenter, and then at the end of the entire PDR, there'll be additional time for any extra questions that did not fit within that time frame. So our presentation order will be structures, aerodynamics, propulsion, avionics, recovery, and finally payload. Also note that we passed out a review item disposition at the tables, and for those of you online, just feel free to ask questions in the chat on the YouTube live stream. All right, and I'd like to now pass it off to our structures lead, Ethan.
All right, hi everybody. My name is Ethan Butler, and I'm the structures team lead for the Spaceport America Cup. And so I'm just going to take you through today, kind of what my team does, what we're going to do this year, and how we make decisions on why.
We're going to stop real quick, try and figure out the audio, hopefully get that sorted out. Seems like people are having trouble hearing. All right, does that sound a little better for everyone? Testing. Does that sound any better?
No.
Feedback.
Joe says it's nearly unlistenable.
Is that any better?
Yeah, that's likely. Can't really hear anything.
Okay.
Which microphone are we using for that?
Podium.
What if we just turn off the podium mic and just talk directly into the computer?
I don't know if there'll be any audio.
I think the issue might be that the stream is like taking the audio from that mic, but then that mic is also projecting it out here. I think it's hearing it again to the mic.
Oh, can you mute
So
the?
are you able to turn the speakers off?
Does that sound a little better for everyone?
How delayed is it?
Is there any audio right now in the stream?
Doesn't sound good. Yeah.
That's better when you said that.
That works.
So the speaker is the problem.
Feedback.
Yeah, it sounds good.
Sounds good. Okay.
Yeah. That's
All right. Sorry about that, everyone. We're gonna keep going here. Hopefully the audio issues are worked out. And we'll keep on.
Okay. So, yes, my name is Ethan Butler, and I'm the structures team lead. So, like I said, I'm going to take you guys a little bit through what we do on the structures team, how we do it, and kind of the overall trajectory of the project this year. So, the project purpose is to, one, construct the body of a rocket that's capable of surviving, a supersonic flight to 30,000 feet. So, we're going to experience almost Mach 2. So, we'll be going almost 2 times the speed of sound. So obviously we're going to need to have a structurally sound body. Another purpose is to organize and complete the integration processes of other sub-team hardware. So whether that be flight computers from avionics or the recovery system, our job is to have a process that puts all of that together in a way where we have smooth integration on launch day. We can get it done quickly and in the right fashion. And then something else I'm very excited about this year is tensile testing. So this year we're going to do some tensile tests with carbon fiber. I will talk more in detail about it later. But the overall goal of this is to get some material specifications so that we can have more accurate models if we do any sort of structural simulations. So I'm going to move on now to system requirements for the structures team. So obviously, number one is, like I said, how is the hardware of all the other sub-teams? So, like I said, avionics, recovery, propulsion, all the above. So another thing is that ability to withstand loads from supersonic rocket flight. And then 3 is going to be a smooth surface finish to reduce any aerodynamic load. So that does not only include drag, but we want to keep a symmetric cross section so that we avoid any sort of moment or torsion that we might see in the flight. Another thing is that I would like to successfully integrate the rocket within 4 hours. That's just something that I want to see the team do. Last year competition, we ran into a few problems here and there, but you actually do get bonus points for integrating and launching on the first day. So that is something I really would like to see. I think it's very attainable, but it will challenge us. So then moving on to the system overview. So this is just an exploded view of our rocket as a whole. And what you're going to see in the red highlights is parts that my team actually fabricates or assembles. So over here, starting with the fins on the left, those are aluminum and we use a fin kit. So we do not fabricate those ourselves. However, we do assemble it. And it's quite an involved process. It's a lot of feel, and it gets pretty challenging, as we saw last year competition. And then moving over, we have the motor tube. So that's something that propulsion works with, and we make that and get it ordered in. The transition right here in the middle is going to be fiberglass epoxy composite. And so we can use fiberglass there because that's where avionics is going to send signals which can't get through the carbon fiber. So that is what transitions our rocket from the motor tube to the actual diameter of the whole body tube. And then next you're going to see the coupler is this little piece right here. And so that's going to take a lot of the loads from the flight. That's something that I believe we're getting milled this year. And then moving to the right further is the integrated systems bay. So this is going to house things like the flight computer, payload, and things of that nature. So inside of this, you can see rails right along there. So we're going to make those out of carbon fiber this year. And then also right at the top and the bottom are bulkheads. So that just helps us section off the rocket. And those are also carbon fiber epoxy composites. And we are using a honeycomb material in between them this year. And then further down is going to be just the body tube. So this is another carbon fiber composite and the nose cone. So that's going to round out the whole rocket. So just like I said, some student fabricated aspects were the body tube, nose cone, transition piece. We call the integrated systems bay an ISB. And inside that, we're going to have bulkheads and rails that are carbon fiber epoxy. And then we have the recovery bulkhead, which is right up here. So that will house recovery charges that blow the nose cone off. And then lastly was the fin can assembly. So this is just an all-inclusive view of what our rocket is, what's inside of it, and what parts we actually make and what they're made of. So moving on, in the structures team, with the nature of the team, there's not too much new design from year to year. Grant, like with that being said, there is part nuances and process refinement. So this year we will be utilizing old processes from years prior for the most part, but we're trying to make a shift to be more data and engineering driven. So some processes that we're going to be utilizing will be carbon fiber epoxy layups, which I'll talk about a little bit more, fiberglass layups, and mold creation. And so if anybody's unfamiliar with carbon fiber epoxy wet layup is what it's called, is you take carbon fiber fabric, which is just like any fabric, it has different strands of carbon fiber woven together. And what you do is you mix epoxy and resin, and then you infuse it into the fabric, whether that be with scrapers. Sometimes we use paint brushes. So you want to make sure that the fabric is actually soaked thoroughly. And then basically you let it cure and it becomes a solid structure. So we will be utilizing those general processes. But as I said, we're really trying to push like data-driven reasoning. And so that brings me to new things we're going to do this year, which are number one, we're going to lay out parts on aluminum panels. So you can see over here on the right that we did a layup. These are bulkheads, and you can see that it's on an aluminum surface. And so there's a few benefits to that. One of them being that the parts are a lot easier to get off. Those parts just come right off because you can prep the surface very well. Another thing is the surface finish on the side is very smooth. It's almost glossy right off the bat. And then it also helps a lot with our vacuum bagging process, which is what I'll discuss next. And so you can see over here on the right, this is a vacuumed bulkhead process. So outlining this panel is yellow vacuum tape. And so what you do is you put that down, and then you do your wet layup here, and you can see there's kind of like almost a plastic wrap that you line to the tape, and you basically stick a vacuum pump in it, suck all the air out, and it compresses the parts down to squeeze out any extra epoxy or things like that. So something we're going to do is try and vacuum bag all of our parts, so that be the body tube, the nose cone, the bulkheads, the rails, everything. So that's going to lead to tighter tolerances, and it should help us have an easier integration. And so another thing that we're going to do this year is the use of this honeycomb material down here. So in prior years, we had done plywood. We did carbon fiber, plywood, and then carbon fiber again for bulkheads. And so this year, we're trying out the honeycomb material. So one of the advantages is that it's lightweight. So we didn't reach our altitude last year, so shaving off weight wherever we can is big. Another thing is the use of plywood wasn't exactly the most engineering, I guess, sound thing. It was a very good decision at the time, but now we have honeycomb, and so we want to use the structural advantage we have on this. So honeycomb material it's very interesting. You can bend it, you can cut it, you can rip it, but on a certain axis that is normal to the surface, so coming straight off of the surface, it's very strong. So you can actually stand on this paper-like material, and it holds up. So we're going to use that to our advantage, using the bulkheads, because there will be some compression, especially when we have recovery charges blast off the nose cone. So there will be a little bit of compressive forces down on the bulkheads, so it will be structurally sound. So moving on and talk about the tensile testing. So we created test coupons, and we're using the ASTM D3039. So that's just a standard for testing composite material. And you can see them over here on the right. They're slightly bowed, so we are actually remaking them so that we can have a uniform cross section, because we want to make sure that if we're going to do the test, we want good data. So we are making those again right now, and we will be testing both a plain and a 2x2 twill weave carbon fiber. So how carbon fiber works is it's woven in different manners. So plain weave, you can think of it as a checkerboard, and that's more rigid. So it works great for things like bulkheads, things where you don't really need to mold to a certain shape. But the 2x2 twill weave is actually very flexible. You can move it a lot like that. And I really want to take this to our advantage and use it in the nose cone this year. So we do want to test that, make sure we're not losing anything by going to a different weave. So we will be testing both of those this year. And we will be utilizing relations at the CDME, which is where we do our work to tensile test. So as I said before, the whole purpose of this is to allow for more precise analysis, so we can get things like Young's modulus and Poisson's ratio, stress strain curves, and so that's just going to increase any validity of our structural simulations and just give us data-driven material characteristics. And we do want to compare those with old results and what the supplier is telling us. And lastly, it was a great way to introduce the team to carbon fiber epoxy layups. So the team did a great job And I think going forward, we'll just have a lot more experience and be able to do things quicker and more efficient. So with any project, there's obviously risks to success. So it is important to identify them. And I'll speak on the next slide on how we're going to go about mitigating these risks. So first is time shortages. So everybody has a busy schedule. And sometimes with the nature of the team, every meeting is a build meeting. So you can have a few hour meetings. But it's important to stay on track. So we have to make sure that we don't fall behind and then are pushing at the end of the year. Fabrication errors is another one. So that could be a poor layup that's leading us to an out of tolerance part. So you can have breaks or cracks as well. C being integration failures. So as I mentioned, integration is the process of putting together the rocket. So poor processes there can lead us to pushing things in the rocket, not a smooth fit, and we can then break things, which is not ideal on launch day. And then lastly, our test launch failures. So that could be a crash landing or any structural failure. And that would lead us to refabrication of components. We would have to do those very quickly, which again is not ideal before a competition flight. So this is the risk matrix, and like I said, we're going to talk about how we're going to mitigate these risks. So first, like I said, the time shortage. So that is unlikely, and it is a minor risk because if we run out of time, we simply have to have more meetings and just pick it back up. So how we're going to mitigate that is just make sure we have a strict timeline and we stick to it. And that as the team gets better, we make sure that we're efficient and that we can get parts done in a reasonable time. So B is going to be fabrication errors. Again, that's an unlikely error that is probably minor. And that's because we can remake a part. But to mitigate that, we're going to be using a detail-oriented mindset. I really want to make sure that I prep the team before we make every part so we know what they're doing and how we're going to do it. And that way we just don't risk any sort of breaks or cracks or things like that when we're so C would be an integration failure. And well, that's unlikely that is significant because on a launch day, if, like I said, you're pushing things into the rocket, they're not fitting, then you break something, that's not great for your launch that day. So to mitigate that, we're going to make sure we keep tight tolerances, and we're going to have well-documented procedures and label our orientation lines. So we want to make sure we have checklists, order. We want to make sure we have everything documented so that day of we just follow an order and we're good. And orientation lines are when you're putting together the rocket on the table. You want to label lines so that you know exactly how you want to orient everything every single time, and that there's no thought of, oh, maybe we should have shifted it 180 degrees or anything like that. Everything is just lined up perfectly. You have a successful integration. So lastly is a test launch failure. So that is unfortunately possible, and that would be a major risk to project success because of the time shortage at that point. We would be having to refabricate basically the entire rocket in a month or two. So the only way to mitigate that one is to ensure our processes are very efficient. So that way, if it comes to it, our team can just hit the ground and run. We can make quality parts in a quick time. And so that brings me to the schedule for the year. So over here on the right, you just have the months and when they're going to get done. So tensile testing is going to take place this month and through November. So we're going to be doing the testing and analyzation of any of those results. We did lay up the bulkheads and we actually cut them already. So that was in October. The first major rocket component is going to be the body tube. And so next meeting, we're actually going to prep that layup and we're going to get prepared to go into that. So that will be a little bit of October and November. And then as we get towards winter, we're going to be creating molds for our transition piece and our nose cone. So because of the contours of those shapes, we do need molds. And so we actually create those ourselves with shapes that were given from the aerodynamics team. So we will be doing that hopefully before Christmas break. And then that will allow us to, when we come back from Christmas break, lay up the transition piece, the nose cone, ISP rails, everything. So we're gonna be doing that. I want all those parts done by the end of February. And while that's occurring, we're gonna be prepping those parts. So sanding them, cutting them to tolerance, things of that nature. And then in March is actually the test flight. So after that, hopefully everything goes well, and we will perfect those components for our competition flight, and then we will go to the competition. So with that being said, I'm going to open up to any questions.
Yeah, so I got a question on the bulkhead. You haven't done this before, right?
The honeycomb, I don't believe so. I don't know if you're aware if we've used them ever before. I know we didn't
We've
last year.
attempted it in the past, but we've never made it work. So we're trying to iron out this problem.
So you thought, so the next question is, what's on the face of the bulkheads at the end of the honeycomb?
So this is actually the bulkhead layup. So basically this piece of honeycomb is sandwiched between 3 layers of carbon fiber,
Okay.
cut at different angles as well. So
But they're going to be circular, right?
yes,
Okay.
so we cut those last meeting. I actually didn't take a picture of that. I should have. But so those are circles now.
Okay.
So we cut those. And in the past, the problem was that the carbon fiber would peel off the honeycomb. But I think because of the vacuum, it worked really well. So you could see all the epoxy kind of like fusing out of it. And even with the cut, it stayed right on top of it.
So are we going to do compression testing on those?
I hadn't planned on it, but that's actually a really good idea, especially with the recovery charges going up. That's something I would definitely look into, actually.
That was actually my question too, because forget the ejection charges, that's low pressure. It's when you start pulling on those with your threaded rod, you pull them and you're crushing the interior,
Mm-hmm.
and now all of a sudden you got stuff loose on the inside.
No, that's actually a good idea. I guess, so do you guys have any suggestions on how you would go about setting it up, like the test like?
I've seen people do that, they use inserts.
Okay.
So now that's on much larger scale than what you guys are
Yeah.
doing. So I think it's easy enough if you put a bolt in there and start torque wrench on there,
Yeah.
or see
Okay.
where it's crushing.
Yeah.
At least that's basic. Yeah, that would probably be the only worry is tighten those down and they crush a little bit. Any amount of flex is just gonna make it loose.
Yeah, exactly. Okay. That's definitely something.
I've seen guys make beds out of it. I haven't seen actual structural bulkheads out of it.
I was going to say, just, put on a flat surface and have a big rod and put a bunch of weights on the top.
Yeah, it's true. So we get the exact power.
We don't have any more questions here. We have one question in chat. Casey asks if we have any plans to verify that the shorter coupler can take the loads caused by the blade.
I will be honest, I'm going to defer that one to Zach. Zach's been working on the coupler.
There's no destructive testing at the moment. We're going to try and do NDA analysis on that and hopefully get some better. But nothing at the moment.
And we've been, ANSYS, the simulation software, just came to our last meeting. I talked to them a little bit about some structural simulation. So hopefully we could maybe do a little bit of that on the side of the
How long did it take you guys to integrate, since you brought up integration? How long did it take you to integrate it out in New Mexico? I don't remember.
I think the thing can added a couple hours to it, but before that,
Well, but that was all with the hotel thing. So,
well,
I mean, at the field.
it wasn't like the Finky was.
Well, I wasn't.
Yeah, because we had to hit it with like a.
Who told you to do that? That's what I was just wondering is how long it took you at the field.
I think it was about 3 hours.
But So I put 4 just because I want to make sure. I think 4 gives us a lot of cushion to still launch that day, especially for their time.
Let's do the thin can here this year.
Yeah, exactly. Bring it assembly.
Just one more comment. Your schedule, we're glad to see you have a schedule, but it's not month-to-month schedule.
Yes.
Especially when you get later on in the game, you're gonna need probably a week schedule. Maybe even day-to-day near the very end.
Yeah.
So
So
we're gonna have to, review it probably, maybe not now, but somewhere in the middle of it later on, every week, because, you call it a time shortage. But the whole purpose of the schedule is to, estimate, how long it's gonna take, how many man hours, and then if you start to slip, then you have to make some corrections. So a time shortage is only happens when you're not managing the schedule.
So at least for right now, we have a monthly leadership meeting, so I kind of readjust my schedule every time we meet, and then so I have my own weekly schedule
Okay.
that I stick by for meetings. So I do have those details,
Okay, great.
but this is just the general trend, I guess, for the year. But that is, I like doing that because I have a weekly schedule that I want to do this at this meeting, this at this meeting, and because obviously you have to be detailed, otherwise you're gonna run into that for sure.
And make sure you have a critical path.
Yes.
Because critical path is what you want to measure, because if something slips in the critical path, the endpoint slips.
Mhm. Is that no more questions?
There was another question, but it was answered in the chat. Casey asked what the plan was for our fin can and if we plan to use the same COTS product. The plan is to use hopefully the 4-inch version of the same COTS can.
Yeah, and we want to make sure that we assemble that fin can here on campus before we bring it to competition, so that way we don't run anything like we did last year.
I have a quick question.
Yeah.
I know we've talked a lot about the normal stress of, sorry to go back to the honeycomb thing. But I know we talked a lot about the normal stress there, but I recall last year during integration, there's a lot of even shear stress on those bulkheads from us trying to jam things in there. So has there been any consideration as to the shear strength of the honeycomb and whether that might become a factor during integration?
So honestly, that was my main thing. Is I want to avoid that completely by, like I said, with the tight tolerances. That's why we vacuum, so that we don't have to, like last year, jam things in there. But I think the shear strength should be fine. We cut them, and I kind of just messed around with them a little bit. I really do think it'll be fine. But for integration processes, like I want to make sure we don't have to jam things in there. So we're gonna make sure we cut things to tolerance, and everything is the shape that it's intended to be. And that's with the orientation lines and everything like that.
Gotcha. Thanks.
All right, with that, I'm gonna pass it on to aerodynamics and Sawyer.
We're not using the microphone. All right, hi guys. My name is Sawyer Ahmed, and I'm our aerodynamics. So my sub team's primary purpose is we want to gain insight into how the rocket performs just throughout all flight regimes, primarily in terms of drag and stability. We want to be able to accurately calculate what the rocket's peak altitude or apogee is going to be during flight, and then we want to teach our newer members pretty much how to utilize computational fluid dynamics. So our system requirements are that we need to analyze the rocket's drag and stability characteristics pretty much throughout all speeds. And then based off of those results, we want to recommend geometry changes to optimize our flight. And then we want to acquire drag coefficients throughout all speeds as well, and then utilize them in order to predict our rocket's altitude later on. Design process. So again, we want to teach our team how to utilize computational fluid dynamics, and then as a team with our we primarily use the CFD software ANSYS Fluent for analyzation. And then with that, we want to determine drag estimates, again, throughout all speeds as a team. And then additionally, we want to assess the stability of the rocket, primarily using angle of attack. And then later on, with our computational results, we'll want to verify those probably through wind tunnel testing and then hand calculations as well. And based off of all of those results, we want to recommend geometry changes. So how most of our analysis is done is we have this, it might be kind of hard to see there, a little 2D half cross section of our rocket. We have that, we use that as a boundary sort of, and then we have this as our computational domain. So we'll import this to our CFD software and pretty much just simulate at different speeds the flow going over the boundary of the rocket. And then after we run those simulations, we can pull out results like this drag coefficient residual. You can see where the drag coefficient kind of converges on this graph, and that we can use that result to see just the drag coefficient at whatever speed we're testing it at. And then you can't really see it too well, really at all on here actually, but we can pull out pressure contours as well and just see pressure distributions around the rocket. And there's other things as well we can look at, like temperature, speed, and density. So these are just some results from last year doing a 3D quarter body test. This was tested at Mach 1.7, which was at our max dynamic pressure. And our meshing was, the results were at about like a Y plus of 150, which is just kind of describes how fine the mesh is close to the wall, depending, we want that to be at a certain amount, depending on whatever turbulence models we're using in the software. So these are just some drag results from near the end of the year. And we have a drag coefficient here, and then there's some open rocket results as well for comparison. Pretty much during this year, we're just going to be looking at reducing these drag amounts as much as possible. Risks to project success. So first, we have errors from meshing inaccuracies. Depending on how you make your mesh, it could represent the computational results poorly. So that could throw off our results a lot. Over and underestimation of drag. If we overestimate our drag, we might end up accidentally making a heavier rocket. If we underestimate our drag, this could lead to some serious failure during flight. And then if we incorrectly estimate our drag, we won't be able to correctly calculate what our apogee will be as well. Wind tunnel testing access restrictions. If we cannot validate our computational results with something like wind tunnel testing or hand calculations, our computational results they're not as really reliable if we can't verify them with like real world tests. And then time shortage, we need to work quickly as a team throughout the building stage. So we've got our risk matrix here and our mitigations. As far as meshing inaccuracies go, we can try to validate our meshes with our Y plus values again, just to verify that our meshing will accurately represent how the flow goes over the rocket, and our Y plus will just vary depending on what turbulence model or all functions we're using to calculate our flow. Over/underestimation of drag. Again, we'll be looking into wind tunnel testing for our rocket to try to verify our computational results, hand calculations as well. if we move on to some 3D simulations later on, we can incorporate a Z, like our results in another axis as well, because primarily what we use are 2D simulations. And then we can test many different flight speeds and compare those to open rocket results as well, like I showed on a couple slides ago. Wind tunnel testing access. We're going to work on contacting faculty that have access to those wind tunnels early on. And time shortage, we just need to work efficiently as a team, divvying up as much work as we can as possible. Then we have our risk matrix here. Primarily, our main concern would be estimating our drag incorrectly. And then second priority would probably be being able to verify those computational results and moving down. We have our mission inaccuracies. We're not super worried about those as long as we go back and check that our meshes are okay. And then we have time shortage, which I'm not super worried about, as long as we can all work together quickly. Here's our schedule for the year. We've started out just with teaching newer members how to use the CFD software ANSYS Fluent. Additionally, we've started and we're moving on to nose cone research and drag analysis, just looking at a different nose cone shape. It might be beneficial to us. Transition piece analysis and adjustments. We're going to have to make very slight changes to our transition piece, like the part between our body tube and motor tube, just because we are increasing our motor tube by like a very small amount, up to 4 inches. Later on, after we've done all our testing for our nose cone and transition piece, that's when we want to verify our computational results with our wind tunnel testing and hand calculations. After we've done that, we've made our geometry changes. We're going to work on determining drag coefficients for the rocket at all flight regimes so that we can as well develop accurate altitude calculations. And then after we have our test flight, we'll use that to go back and verify our altitude calculations. Okay. Any questions?
Yeah.
Yeah.
I'm going for wind tunnel tests is a good objective, but I don't think you're going to be able to find some place you can do it. But if you do, good for you. What I would recommend is you must have some flight tests from either last year, year before, or this year.
Yeah.
And so that's the best place to get the flight test data. The tricky part about numerical calculations is at the base, because the flow comes back and it separates at the base. And so you don't probably have a very good idea what the pressure is on the base. So the base pressure, you can kind of use that as a residual, because the pressure drag and the skin friction drag, those are pretty well known and easily predictable. So actually, I took a look at base drag a couple of years ago, and I can share what I found with you. I had a bunch of old data from a book by a guy named Horner, and I think I basically came up with pretty close to what you had 2.9. I think it was like 3.0 was kind of the right number. But anyway, the base drag is the tricky part as far as I'm concerned.
Yeah, we definitely do need to look into that. And then as far as your comment on the wind tunnel testing, there are some subsonic wind tunnels over in Bowles Hall on campus. So we could use those up into an extent. And then as far as like into the supersonic region there, I don't know if we'll be able to get access to one. But I think there are some at the Aerospace Research Center at OSU. I don't know if we'll be able to get access to those. But we can analyze our past flight data as well. Yeah,
it's worth a try.
Yeah.
That was just a small personal note. I was one of the first people that went to work at that Aerospace Research Lab back in 1965.
Nice.
Moved the shock tubes from what's now Bowles Hall out to the Aerospace Research Lab, but those shock tubes are long gone, but they do have a supersonic tunnel out
Yeah, okay, yeah.
there. I don't know, big enough.
I don't think we could fit our full rocket. Make a small model, yeah.
Do we still have the flight data from last year? There you
Best thing to use.
Yeah, that's easy. Because you got burnout speed.
Yeah.
I think that is it from the telemetry that you've got it.
How do we have that?
Yeah, telemetry will give you pressure and temperature. That gives you your density number and everything else. That's a good way if you look at the data from last year that your team did.
Yeah.
Compare it. I mean, acceleration might be hard because you don't have motor data, but deceleration, you have speed of burnout. When it gets to the top, that should verify your numbers pretty close.
Yeah, that would be useful. I think primarily we would want to use the wind tunnel testing because we have the flight data from our design from last year. If we want to make any new design changes, that would be useful. But I guess
Well, at least, because you're not changing anything in terms of your measuring anything from last year.
no, yeah.
So if you verify the data that was predicted last year versus the actual data,
Yeah.
then you know where you're making mistakes.
Okay, yeah.
So, actually, you hit just about all my questions. Modeling imperfections. That would be what I would be curious about. Just obviously, we didn't have anybody on the team who's data to body shop last year to give us a nice smooth finish. And there's always spaces in between transition, nose cone that are never perfect. How do you model that into the?
I don't think.
I assume surface drag of some sort, but
Yeah, I guess we can do that. I haven't done much of that up until this point. Primarily, I've just looked at drag differences like between different designs, not what happens if there's like surface imperfections.
you'll get all kinds of standing shock waves off that.
Yeah.
Some worse than others.
Great, that's all the questions we have from the audience here. We do have one question in the chat. Casey again asked how fast can you iterate simulations to keep track with rocket weight changes, and do you have any plans?
What was the question again?
I'm sorry, I said I kind of fast. How fast can you iterate simulations to keep track with rocket weight changes?
I'm not sure. I think hopefully fairly quickly with how many people we have on the team. I'm not sure. As far as improvements go, I know we had a much smaller team, aerodynamics team last year than this year. So with at least preparation on my part, hopefully we can show up every meeting and just knock a bunch of simulations out every day with how many people we have.
And that is all the questions from the chat. He also said note on the painting, he can't fix a rough face. Standing is important. That's weird for structures.
Is that it? Okay, well, I'm all done now, and we're moving on to propulsion.
Hello, everybody. My name is Noah McGillivray, and I'm the propulsion lead. So, the purpose of our team is to research, design, develop, and test the solid rocket motor. as well as giving students all the all the hands-on experience with propulsion test systems. Apologize for the voice, I'm a little congested. Structural hardware. So first we have the motor case. It's made out of aluminum, 4-inch outside diameter and 54 inches long. Currently, that length is subject to change. We have the forward closure. This piece seals the forward end of the case, seals all the hot gases in. You can see that hole on the top. Hole on the top there, that's where it connects to the rest of the rocket. And then we have the O-rings and retaining rings. If you look, you can see the grooves on the forward closure. That's where the O-rings are used to seal, to create the seal between the forward closure and the motor case. Then we have our propulsion hardware. We have our nozzle. It's made out of graphite. It's based on specific machine diameters that we determine using motor simulations, using the software called BurnSim. You can also see these grooves here, once again for the O-rings, for sealing purposes. And these are our solid propellant grains. This is the fuel of the rocket. We stack 8 of them into a motor case, and that inner core acts as the combustion chamber. So the objectives this year, we at competition last year, we suffered a loss in our altitude, compared to our expected altitude. I think we were about 6,000 feet underneath 30,000 feet. So to combat this, we want to increase the amount of propellant in our motor so that we can increase the thrust and hopefully attain that 30,000 feet. We decided to go from 98 millimeter outside diameter to a 4-inch outside diameter, and we estimate this to give us a 20% increase in thrust. I don't have it in here, but we're also considering changing the overall length of the propellant. Currently, we have simulated at 60 inches, but I'll get to that in a later slide. We have 2 propellants that we're interested in possibly using this year. First is the BSLI white. Metal fuels are 6% aluminum and 2% magnesium. And then we have our BSLI red, which is 3% aluminum and 11% strontium nitrate. As always, we want to prioritize the reliability of our propellant over our altitude goals. You know, the altitude doesn't mean much if we can't get off the pad, or if we do get off the pad, just not in the fashion that we really want to. Always continue developing our static testing skills. We can modify, if needed, all of our testing procedures. And this says acquiring data to characterize motors. We probably will not be doing that this year. And the reason for that is because now that we have an even larger motor, 4-inch motor, when you do small characterization tests, say of 54 millimeter or anything really less than 98 millimeters, the motor performance does not scale linearly with the size of the diameter of the motor. So it can kind of be a waste of time and a waste of money. We also want to investigate bringing our motor development to OSU property. Currently, it is done in Dayton, which, you know, traveling, the commute is not ideal. It restricts our ability to be flexible with our dates when we want to make the motors, when we want to test the motors. So the Aerospace Research Center has facilities. Historically, we have been able to do some subscale motor testing there, but they're only large enough for a 54 millimeter motor. So when we do get back to characterizing a new propellant formula, we would like to investigate that as a possibility. Our design process, we use a lot of literature, obviously. Not a whole lot other resources out there for making motors. So primarily we use Experimental Composite Propellant by Terry McCreary and Rocket Propulsion Elements by Sutton. To simulate the performance of our motors pre-static test, we use the BurnSim software. It gives us motor characteristics like burn time, total impulse, gives us a thrust curve, a pressure curve, mass flow rates, and to do that, we use, it's a little hard to see here. I doubt anybody can see it on the YouTube stream, but we insert the grain geometries for each grain, the length, the diameter, the core diameter, and we input our formula into the software, and it kind of just spits out these curves, and it spits out an optimized nozzle based on this data. And then we also reference historical BSLI data. Like I said, last year's motor was not able to get us to 30,000 feet. There are a couple of reasons that could have happened, which I'll get into later. We also want to use our existing data from our 98 millimeter motor test as a reference for performance scaling. Because 98 millimeters and 4 inches is so close together, I think it's 3.6 millimeter difference. So yeah, you can see this is our actual data that we've obtained from one of our subscale L motors for the BSLI red propeller. So this is currently where we're at with our motor. Very early in development, but this is our BSLI red 04028. That's 4,028 newtons of average thrust. You can see here, we have the 4 inches and the 60-inch propellant length. Usually we go with 48 inches of propellant length. So it's quite a big increase, and you can see that in these numbers. The total impulse, pretty large. It's about, I think, 3,000 more than the 98 millimeter. So it's about 24,000 newton seconds. Max thrust, also large, 5,100 newtons. Burn time, pretty standard, 6.11 seconds. And the max pressure is pretty low, as simulated in BurnSim, but we definitely expect this to not be very accurate. It hardly ever is. The pressures can get up to anywhere from 800 to 1,200 psi. It kind of just depends on how the test goes. If there's an anomaly, sometimes the case can get very pressurized, and your max pressure will be much larger. And this will bring us to an estimated altitude of 41,000 feet, which again is why I said this is so preliminary. That's 11,000 feet more than we want. So we will probably change this. We just haven't gotten to running all the simulations yet. We will probably change this from 60 inches to maybe back to 48. We tried simulating the 4-inch motor for this at 48 inches, and we were not able to get to 30,000 feet still. So we're going to have to make it longer than 48 inches. So the parameters are destined to change. Oh, and this is a static test of our 98 millimeter from last year that we used. It's not the one we used for competition, but this does use the BSLI red propellant. So you can see here, again, nobody online can see this probably. Max pressure was 866 psi. So this is probably pretty accurate. Risk matrix. So we have a few risks, a few notable ones. First and the most obvious one is the explosion of the motor, also known as a CATO. And the way we plan on mitigating this is by static fire testing our motor. There's not a whole lot much more we can do. Events like this severe, like the explosion of the motor, are pretty unpredictable, and they can be caused by a variety of anomalies that one might never expect. So take our precautions, do some static fires, have a test flight, which would be especially important, and we'll do all of that using the full-scale hardware. That, very rare, but very, very severe. Especially if it happens in competition, that would be the end of our run. Then we have a chuffed ignition or a failed ignition. A chuffed ignition is when you aren't able to, well, you try to light it, the igniter, and some propellant may light, but the case doesn't, it's not able to get up to pressure quick enough. And so it kind of just sputters. The pressure rise isn't large enough for the rest of the propellant to catch flame and to keep a good burn going. So a lot of this comes down to practicing proper igniter placement. Preferably, it's usually down toward the bottom grain, if not in between the bottom two grains. This would be, it's a possible risk, but minor impact because you can always simply relight the motor. If too much propellant has to burn. This letter C, spinning the motor liner. This is a problem that we've been having, or that we had a few times last year. So the motor liner, we used to use cardboard motor liners, and it goes in between the propellant grains and the inner diameter of the aluminum motor case. So when the propellant burns, some of the liner can break off without burning completely in the motor. And with all of that high velocity gas and pressure, it can spit out chunks of propellant or chunks of the liner. And for the split second moment that liner is in the nozzle, in the throat of the nozzle, you have a very large area restriction. And very quickly, the temperature in the case will go up and the chamber pressure will skyrocket. And when you have temperature increase and pressure increase, all of your propellant is going to burn up real quick. So we have a theory that this may have happened in our competition flight, which would explain why, there were some visual reports of an anomalous looking burn. And it would explain why maybe we had a lot of propellant burn up in a really quick time period. And we weren't able to get enough thrust from the rest of it. And then D, we have casting failure. This is pretty unlikely and would also have a minor impact. I think the main impact it would have is to our budget, because casting these things is not cheap. But we can always simply cast them. Plan for the year. I actually think this is a redundant slide, so I'm going to go here. Yeah. So researching the motor improvements, casing size, composition, nozzle dimensions. That'll take place from now until December, as will reestablishing that contact with the Aerospace Research Center for the 54 millimeter motor testing. And right now we're also running through all of our preliminary simulations and getting ready for testing. And by the end of December, we want to have, or by the end of March, we want to have our motor design finalized completely, including hardware like ordered, and And in February and parts of January, we really want to get early static tests in, so we have a large margin afterward to work with that data and see what we need to do to optimize the motor's performance. And we want to have our static tests in late February, early March. We want to static test both the BSLI red and the BSLI white propellants to see which one better fits our needs. And by the end of May, obviously, we want to have our competition propellant completely determined, whether or not we're going to use the red or white, or possibly something that we haven't even thought of yet. Maybe we need a new propellant. Questions?
This is just, I don't know if it's off topic. I thought about this week. Scott Lab said absolutely not, that we can't fix
They said no.
I'm asking you, Zach.
I
Is that
don't
an
think
issue?
we've asked them.
I know that we brought it up with them at some point. I think
That was a while ago.
3-4 years ago. Check anywhere on campus that'll let us mix. I think we have to worry about dusting is the only real hazard. And since it's such low quantities, the reason I brought this up was that there's a group out at Iowa University that they started letting them mix on campus. So we might have somebody to help out, but ease the fears of the people that are running facilities here.
Yeah, I'm not sure. I think a lot of it is sort of non-negotiable with them. I think it's either just black and white, yes you can, or no you can't.
They say stuff like that, but then they have a gallon of gasoline or kerosene laying around in the lab that's 1,000 times more dangerous. So a lot of it is convincing them.
Yeah, for those online, I'm not sure if you could hear Todd's question, but he asked about bringing the motor mixing, the actual casting of the propelling brains to campus. We've had issues with this. Obviously, the university isn't very fond of us mixing propellants on campus, but we are going to do our best to try and bring that closer to OSU as well as the static testing, because that being in Dayton as well really restricts how many people we can get hands on with this kind of process. So we definitely want to get that closer to home.
All right, and if there are no more questions from the audience here, the question from the chat says, have you investigated the instrumentation issues faced in the test stand last year? Are you trying new sensors, new PDA?
We have not. We haven't really talked about a new data acquisition system. We are going to order a new load cell, and the pressure transducer seemed to work fine for the most part last year. That's a good question though, because we have had some difficulties using this data acquisition system. It's kind of, I think it might be aged out at this point. I think we might be due for an upgrade. That's definitely something. Any questions? I'll give it up to the avionics lead, Peter Hall.
Hello, everyone. I'm Peter Hall. I'm the avionics section lead, and I'll be walking you through the electrical systems of the rocket. The purpose of our project is to design and build and develop a electrical hardware and software system, which does two main tasks. First of all, to control the parachute deployment for the rocket's recovery, and secondly, to collect a lot of data for live telemetry purposes that we can track the rocket while in flight, and also we can do some analysis afterwards to find out what might have went wrong, what can be improved, and that sort of thing. So we got some system requirements. The most important one is to deploy the drogue parachute at apogee, so at the highest point in the rocket's flight, and the main parachute at approximately 1,500 feet. That number is subject to change based on the work from aerodynamics and the other sub-teams. Another big thing we always try to do is, or we will do, is to have all of our critical systems be fully redundant so that we can ensure that our recovery will happen and we don't lose the rocket in mid-flight. A new requirement for this year is we're going to be using a student research and developed, or SRAD, flight computer as a secondary altimeter. This is something new we're trying this year, and I'll discuss more about it in a little bit. We track and transmit accurate and high-resolution telemetry data using, against SRAD software. So this allows us to, while the rocket's flying, we can see its altitude, we can see its position, helps us with recovery because we know where it landed. And also, in the event that the rocket does experience some sort of like catastrophic failure during flight and we can't recover it afterwards, we might be able to figure out what went wrong because we are recording this data up until the point of impact. Some extra things, we like to collect flight video. This is mostly just so we can get an idea of what the rocket looks like, or sorry, what the rocket's seeing. It's pretty cool. It's kind of a fun thing we like to do. Also the arming, so I'll discuss arming in a little bit as well. We can control that remotely via radio, so that provides a safer handling of the rocket as well. And our system this year will fit into a 1.5U CubeSat size. CubeSat is just a number of things, but it's this, a size standard for satellites. Halo gets a bonus for it, and we sort of just stick with that theme as well, so our systems can work together well. Last year was a 2U size, so we're decreasing a little bit to save some weight and space. So for our design process, we like to use previous designs as foundation. This does not mean we're just blindly follow what was done in the past. We do verify each decision we make based on our data and our research, but there is a wealth of knowledge and experience in previous work done that we do like to build off of. A big focus this year in our design process is integration and reliability. Last year, our system was designed in such a way that it was somewhat difficult to integrate with the rest of the rocket. When we were assembling things, we had to move a lot of things around in order to connect our wires and to connect to the other systems. So this year, we're looking to streamline that, working with structures and the other subteams to make sure we can integrate in a way that's not only fast and expedient, but also so we can be certain that everything is set up properly and we didn't forget something. We also like to adhere to industry standards and conventions wherever possible. There's a lot of work done in the field that we like to try and meet. Sometimes it's not financially possible, but when it is, we like to do that. And also, another goal is to engage our entire subteam in the design process, not only so they can benefit from the experience they gain, but also it helps us be more aware of potential flaws in our system and just encourages better innovation. So now I'm going to give a general system overview, and I'll get into more detail about the specific components in a little bit. So the first thing I'd like to start off with is up here. So the rocket and these systems can mostly be controlled from the ground. So on a computer, we have a ground software which we are researching and developing, and this connects via USB to a radio modem, which can communicate with the rocket. So there's a connection there. And specifically what this radio connection is for is to send arming commands and also to receive telemetry data. So all this stuff on the bottom path is contained within the rocket. So just bridging from here, we have our radio telemetry modem in the rocket. It's a very similar model to this one. It's just a little bit smaller. That allows us to just fit into the rocket better. This connects with an SRAD flight computer, which handles a number of things. It handles data collection, but it primarily, additionally handles our communications. So we're receiving these communications here, and then we're processing them in here. Now, this computer is connected to the other components on the rocket via CAN bus. CAN bus is a communication protocol we chose to use because it's exceptionally reliable. Specifically, it's decentralized, so a lot of communication protocols rely on a central host to sort of handle our communications, whereas CAN bus is decentralized, so it is less reliant on the central controller and less prone to failure. It's used frequently in the automotive and aerospace industry for this reason. But the main things connected to this this connection here is our SRAD arming circuit here. So the arming system, basically we have our altimeters, which basically they measure the altitude and then they send a signal to recover to deploy the parachute when needed. And they also can check the nose cone. So these are obviously dangerous systems, and we want to keep those turned off while we're assembling the rocket. We don't want, as they're putting on the nose cone, for us to accidentally eject it. That would be a huge safety hazard. It would also probably damage the rocket. So we have these arming circuits, and basically we can keep the systems entirely turned off until the rocket's safely on the pad, at which point we can remotely turn those on. So that's what the arming circuit here is. We have one hooked up to our commercial off-the-shelf altimeter, which is thus connected to a recovery charge. Now, the innovation I mentioned this year was we're going to be using a SRAD altimeter hooked up to a recovery charge for our second one. We're required to have 2 for redundancy, which is also a goal of our system. These 2 systems, so the SRAD flight computer and the SRAD altimeter, they will be on the same circuit board, except they're electrically isolated for the same safety reason as our other arming circuits with the commercial flight computers. Connected here as well is a camera just for recording flight data. Over on the right, I'll get into this in a bit when I talk about risk mitigation, but we do have an option to add a second COTS altimeter if our SRAD one is not proven to be reliable. Shouldn't need to be using any of this, but it is. Our design is such that we could if necessary. There's also some peripheral components, so these are things that either are working in the background, like our batteries or our power management, or it's just entirely independent of the rest of the system, such as the Atlas Metro IntelliGPS. This is our redundant tracking solution that just provides other telemetry updates to these systems all fail. So to discuss the structure a little bit, as I mentioned before, it's a 1.5U CubeSat design, and there's a key design principle behind this, which is that it's completely, or at least mostly modular. So we have this large circuit board in the back here, we refer to as our backplane, and all of our other boards are plugged into that. So across the backplane, we communicate via the CAN bus I mentioned earlier, and also we supply power to these boards. These boards have a couple of dedicated purposes. This one up here will house the telemetry modem. This one here will house the SRAD altimeter and flight computer. We have our power management board right here, and then on the far left side, we have our commercial flight computer and the arming circuit associated with it. We also have connections up here on this middle bulkhead to connect to other systems of the rocket. The reason why we have these bulkheads in our design is so that if there is any strain on the wires or the harnesses going to other systems, those forces are going to be pulling on this aluminum bulkhead. It won't be contacting our circuit boards directly. So worst case scenario, it would just pull on this bulkhead, it wouldn't like tear apart the board. So that's just a sort of safety feature for our design. So to discuss the COTS or commercial off-the-shelf altimeter, so these are circuits which primarily track the rocket's altitude and some other data points, and they determine when to deploy the parachute. So we deploy the main one at around 1,500 feet, and we deploy the drogue one at altitude, and we can customize the settings. Previously, we flew 2, required to have 2 altimeters. Only one is required to be COTS. Previously, both of them have been COTS. This year, the goal is to only fly 1 COTS altimeter. However, if our SRAD one is not proven to be reliable, we can fly 2 instead. The benefits of this is that it is highly reliable and it's proven. We've worked with it for years. Most of the other teams also use these, so we can be fairly confident they would work properly. However, they have limited data collection possibilities, whereas with our custom solutions, we can collect a lot more data and just also higher resolution and more accurate data. There's 2 examples out here, the telemetrum and the StratLogger. We used both of these in the past year, currently deciding which one we'll use this year based on our needs and goals. The transition piece is the place where we house our antennas. So I mentioned we have a radio modem on board the rocket. Now the body tube is made out of carbon fiber, which is very poor RF or radio frequency transmission, whereas fiberglass is much more transparent to radio frequencies. So this is where we put all of our communication devices. Over on the right, I pictured the transition piece from last year. And as you can see, all of the components were basically just epoxied or glued directly on the inside. This year, we're going to change that design and mount them on a separate piece housed between the transition piece and the motor tube. Something similar to this. This is just a mock-up. We're still refining this design. The big advantage of this is that it allows for greater repairability and user integration. So last year, if one of these components broke, it will be very difficult to remove and replace them without damaging the fiberglass because they were just like epoxy right on there. Also, the judges didn't like it at all, so we're trying to meet that standard as well. Because this is so close to the motor tube, we'll be printing with high temperature materials such as Altum or some similar material. Usually those materials are rated up to around 400 degrees Celsius before they experience significant structural loss. So we should be well below that threshold for the motor, or at least the motor conducting through the couple in this case. So now to discuss the SRAD flight computer / altimeter. So this is an all-in-one system. It collects telemetry and it handles parachute deployment. And this is a new thing for this year. So last year we had a custom flight computer which exclusively handles telemetry. Well, it not exclusively, but it handles telemetry collection and also communication. This year we want to add the functionality of deploying the parachutes based off of that. I mentioned this a little bit before, but we will still be able to achieve the same sort of isolation for safety and reliability purposes that our Army boards and commercial flight computers provided last year. So just mention that here, and this helps us to again reduce or even eliminate the risk of blowing off the nose cone during integration or something like that. The advantage of the flight computer, it allows for more and higher frequency data collection transmission, so we can really tune down exactly what sensors we need. We can determine which sensors we should take priority. So for example, during different periods of the flight, we could choose to transmit more acceleration data during the burn, for example, and then we could transmit other data during other parts of the flight. It just gives us a ton of customization over what data we're measuring and when we're transmitting it. And finally, the reason why we're adding the functionality of the altimeter to this is, in one case, it's an opportunity to challenge ourselves and to showcase our engineering abilities, which is not necessarily like a strict design requirement, right? We could just use the commercial one. However, we have an unusually large team for avionics this year. So I think it's a good opportunity for us to challenge ourselves and make sure that we have to take advantage of our opportunity this year and really just push the limit. Also, given the somewhat holistic nature of judging at Spaceport America Cup, I think this will benefit us a lot in that aspect. But obviously, developing new technology is not without risks. So if we cannot definitively prove the reliability of the SRAD altimeter prior to launch, we can replace it with a commercial one. There is an extra slot designed in our modular bay, so we could swap in another commercial one if we are not certain this will function correctly. Another component of the design is the ground control software. So this is custom software that we use to communicate with the rockets. So we send arming commands or disarming commands, and we also receive telemetry. We're writing this primarily in Python. And the main reasoning for this is it offers us a lot more customizability and control than commercial software. So last year we used Cosmos by Ball Aerospace. It worked pretty well. It just wasn't quite suited for our needs. We had difficulty parsing some of the data. We had difficulty displaying the data, and it just wasn't a super easy to use software. It was, for example, it was very difficult to tell if their systems were armed or not. You had to look through all these tables and read these values. Our new one, I think, allows us to be a lot safer and just display our data in a much more useful way. So some risks to the project success. The primary risk, and I'll get to the risk matrix in a moment, is the SRAD flight computer or altimeter failure or early deployment. So to address the early deployment concern, which would be, for example, if our altimeter triggered a deployment or nose cone ejection still during the ascent, which would obviously be a pretty big concern. We'll be doing extensive testing and mathematical validation, so signal filtering, noise reductions, and really just proving that our system is not prone to that sort of failure. Redundancy, this addresses only a total system failure, but we have two of these systems, so if one just does not work, we still do the other one. And again, if our SRAD system is not able to be proven, we can use a commercial one instead. A second risk is structural failure. So we're doing some pre-launch testing, and we're designing with a high safety factor. Just basically, most of our primary concern would be the frame buckling under the force of the acceleration. That shouldn't be a concern given how we designed it last year. The safety factor was 40 or something. So this year, we're just aiming for something similar as well. Also, launch delays or power loss. So if the rocket is sitting on the launch pad for several hours, there's always a chance that our batteries die on us. So part of this can be addressed by We will only arm the systems until they're ready, so we're not going to keep them on and running unnecessarily. That's another advantage of a remote arming system. And also, we are going to spec our battery such that we can be confident that it has, for example, a 12-hour battery life. So we can be reasonably confident we won't have to worry about internal power loss. Concern or risk D, which is pretty much exactly what happened last year actually, is the disconnection of the recovery harness. So the recovery harness was leading from our bay up to the recovery system to the main parachute bag, and it basically twisted, and Trent will talk more about this in the recovery section, but it twisted and disconnected somehow. And so our main parachute didn't deploy. So two things we'll be doing to mitigate this. First of all, we will design the recovery system, I guess, to avoid, and specifically our recovery harness, to avoid twisting. So we can just kind of entirely eliminate that sort of risk. And also, we'll be designing the recovery harness in a more robust way, using stronger connectors and placements to minimize that. So here's slightly repeated, but here's the risk matrix showing a risk here. So we have their SRAD flight computer failure. That's unlikely, but it's pretty major. If it does happen, we could have some pretty serious problems. The structural failure, that'll also be severe. Again, pretty unlikely, but definitely still an option. Then C and D are rated as possible. The thing is with these, so they're less severe because we could be aware of them, at least. So for risk C, launch delays, and power loss, we can be tracking that. We can be aware of that. Should be able to step in if that's a major concern. But again, the disconnection of recovery harness is possible. Obviously, it happened last year. It's pretty major, though it's not quite severe. Even though this disconnects the drogue parachute so we deploy, so we have at least some slowing. So our plan for the year is in October, we've been working on familiarizing the team with necessary skills, as well as determining the overall design of the system and beginning our software and subsystem development, which will continue throughout November and December respectively. In December, we'll be machining and assembling the CubeSat structure. Leading us into January and February, we'll be doing most of the work assembling our subsystems and completing the software development, followed by final system testing in the spring. And then as we go through this design process, we're performing preliminary testing all throughout. Any questions?
Yeah, so you said you're gonna, the SRAD altimeter, you said you have to make sure it's reliable. So what are you gonna do to make that decision?
So there's a couple things we can do.
Decision point, but how are you gonna do it?
Yeah, so there's a couple of metrics we'll be using. We can do some, so we have a pressure chamber at the CDME where we work. So this is one we'll be testing the system where we can put it into this chamber and we can decrease the pressure in a way that simulates the rocket's descent. So using our barometric sensors, we can do that to verify that. We'll also be doing a lot of statistical analysis. So when we're looking at these sensors that are feeding us all this data, we'll be doing some statistical analysis on that to look and see if there's any anomalies that show up, if there's any sort of noise or unusual behavior which might lead to early deployment or some sort of failure as well. We're also discussing other safeguards, such as in order to make the decision to deploy the parachutes, we might rely on the data from multiple sensors. So for example, we could be looking at the altitude, but also the accelerometer to tell us if it's, for example, descending, right? Because we wouldn't want to deploy the main parachute while also descending. So we can use multiple data inputs, and if not all of them are met, we could decide, or the software would decide not to.
You also mentioned redundancy.
Yeah.
Seems like you have a trade-off of, you got both of them there.
Yeah.
Why not use both of them?
So the idea is to use one commercial one and one SRAD one. Is that what you're asking?
Yeah. Use both of them.
Yeah,
At the
so
same time,
that's,
redundant.
we do use both of them, yes. So how the sequence usually works is one of them fires and then momentarily after the other one fires. So if the first one didn't, for example, then we would still hopefully have the second one firing.
So, but at some point you have to make that decision, right? Whether you're going to use Both, one or the other, right? So you have three options.
So I believe, so it's designed such that we had designated one as the primary one and one as the secondary one. If the primary one functions properly, then the second one will still send a signal to like do the system, except we already have been triggered by the first one. So yeah, I believe by competition rules require to use the commercial one as the primary altimeter. So we're using that, but the secondary one will be in there as a redundant solution.
Okay, so you're gonna use both of them.
Yes.
Actually leads into my question. Does Ezra allow you to use? I know they're real strict with deployment and recovery stuff. Are they gonna let you actually have that wired into the system?
Which wiring specifically are?
The SRAC unit. My understanding was always you had to use 2 COTS pieces for recovery.
So I was looking over the rules and I could have been mistaken, but my understanding was they only specified one of them had to be commercial. I'll check again, but that was the understanding I had.
Yeah, you might check, because that's just, I know that they wrote those rules as part of the level 3 certification rules, where you had to have 2 commercial units
Okay.
in there. So I know that's the way it used to be. So they'll let you fly yours, but it can't be tied into actual live charges.
But the others do them again. They weren't super clear on that either, so I'll check again.
You might just double check. Not that you should fly it, but they may not. They may not allow you to have it tied into actual recovery charges for all the reasons that you said. So.
Yeah, mark in the back.
Have you looked into different connectors at all? And have you thought about doing ground testing on different connectors to see which one might be better?
Yeah, we've done a little bit of research into different connectors. I haven't settled on one that I'm super sold on yet. But yeah, we definitely want to do a lot more testing with that system just to make sure we don't experience the same problem as last year.
Did we get telemetry last year?
We did, yes.
Okay, from this basically the same type of system? Or?
Yeah, so we have telemetry both from our custom flight computer as well as from the telemetry.
That's what I was. I knew we were getting data from the telemetry. I didn't know if we were getting telemetry system.
Yes, we were.
Okay. And what frequency range are you using? I mean, is it like a 900 megahertz
Yeah.
or 70 centimeters?
It's I don't know the exact frequency. It's around 920 megahertz. They assign us. I believe they'll assign us the specific frequency we're supposed to use.
So it's not, doesn't require an amateur radio license.
I think it does. I'm actually not certain on that. I was planning on getting certified anyway. I guess I'm not certain if they specifically require for that frequency, but it's certified in that case.
All right, and if there are no other questions here, then we have a couple in the chat. First, did Ezra give us any real issues in the wireless arming design last year? And Joe actually did chime in on this and said that they interestingly didn't say anything about this, but do you have anything else to comment on?
Yeah, they, I mean, I think Joe defended the system really well when they were interviewing us last year, but no, they had no problem with it really. I mean, I think it's pretty clearly a safer way to do it rather than having to be right up next to the rocket armor systems. So I guess they saw that advantage of it.
You might ask, I'm sorry, you might ask them about this because this has been a hot topic amongst amongst the technical advisory panel that I'm on. Was they've actually started instigating some rules about not allowing Bluetooth and some other wireless systems.
Yeah, we no longer use Bluetooth. I know they used that I think 2 years ago. So ours is entirely like just our radio modem. So
I don't see. They were generically saying any wireless. They wanted a hard switch of some sorts.
I've considered adding a hard switch as well, just for redundancy on the arming as well. So we'll look into that.
Yeah, I mean, you don't have to, but it's just, you might double check with Ezra on that. Because rules have changed.
For some of these questions, we could always post on the discussion board and see if Ezra can get back to us directly. And then a second question from the chat is, are there any concerns for the potential decrease in space available in transition due to the increased motor size?
Not noticeably. I I've done some head modeling with the new motor size that these I showed it a couple slides back. I don't expect it to be too hard. Alright, now it's time for Trent to talk about recovery.
Hi, my name is Trent Warner. I'm the recovery lead this year, and I'm going to get into my presentation. All right, the purpose of our project is to have a successful release of the recovery system, resulting in a smooth descent from apogee. Also, I really want to work on strengthening the team's understanding of the recovery system so they can work on problem solving and helping me throughout the year. All right, system requirements. Ejection nose cone will release at apogee with a gunpowder charge of around 30,000 feet. The drogue will descend the system around 75 feet per second. Around 1,500 feet, the tender descenders will fire and releasing the bag, nose cone, and drogue from the system, causing the main to release, descending the body around 15 feet per second. Real quick, I want to go over what a tender descender is, because I know not everyone might know what that is. So it is a body that has 3 holes in it with 2 pinholes and an ejection charge hole where gunpowder will go in the center. And when the gunpowder is charged, it will fire off the cap, releasing the 2 pins that hold 2 D-links that will be connected to our cords or wire. All right, for design processes, we want to move the gunpowder charges or the tender descenders closer to the recovery bulkhead to reduce interference with wiring. Last year we had problems where wires were tangled or ripped because when anything is outside of the rocket under drogue descent, it should assume that it will be violently twisted or thrashed. So we want to reduce any problems that could cause from wirings getting tangled, snapped, whatever. So we want to move the tender descenders possibly on top of the bulkheads, so the wires only have to go through the bulkhead, and there's no chance of it twisting. Later on, we want to separate the nose cone, drogue, and bag from the main to reduce possible cords tangling, so it will later turn into 2 separate descents. I also want to create a new bag to make the integration process easier and a smoother release from apogee. By doing that, we'll just dimension the bag so we don't have to worry about the parachute or any other system that we're trying to throw into the nose cone, causing an odd shape, creating a lot of friction from the bag to the nose cone, making it easy to rip out when you're when we're at apogee. So on this slide here, I have a little diagram that if you have pulled up, you can see, and I'll go through the process. So we have ejection charges that will be released from an E-match from avionics, causing a high pressure, so the nose cone separates from the body tube at apogee. After that, the nose cone will fly off, releasing the drogue and the bag from the rocket, and it will cause it to descend. And then at 1,500 feet, the tender descenders will charge, releasing this wiring that is connected to the bag, causing the bag to open up. And then this system, the drogue, nose cone, bag system to separate, leaving the main to open up and then cause a slow descent. Some risks that can really affect us are wires twisting or being disconnected, shock cords being cut by the body tube, tender descenders not releasing, nose cone separation, or there's no nose cone separation, and the main becomes tangled, slowing down our separating. or increasing our design rate. Some ways we have gone about or are going to try to go about fixing these are reducing the distance of the wiring or the amount of wiring that we have in total so it cannot twist. For our shock cords being cut, we have like some Kevlar sleeves that we can put around the cords, so extra protection, so the wires don't have to get cut. Tender descenders not releasing is also a really big problem, but we can test that in some injection testing. Also, we will have 2 for redundancy purposes. If there's no nose cone separation, that's also really bad. So we just want to do some injection tests early in the year. Obviously, mating can get tangled, so we want to do a drop test later in the year, and I'll talk about that in a moment. All right. So for the first month or so, we were just working on materials and design, and within the next 2 weeks to a month, I want to have all materials and design be finalized. However, I am leaving this open until the end of this year, so we can still have time to work on it. Develop a system for a drop test, because I have recently gotten in contact with the skydiving instructor to do a drop test to verify if our system works. And he has been very helpful so far, but I do not plan on doing that for a while, at least till starting next year before we do our main test out in the cornfield. Fabrication of the parachute. This goes along with the next couple of weeks. I want to create a shape, and also then later on in the year, after I design the system and work on a mock build-up of it, then I want to build it later. That will be last because we do have pressure parachutes that we can use for the drop test. So creating the parachute is not a priority as of now. Have some injection tests later in the year. Still verify that everything's working. And integration process is mostly going to be making sure everything fits in properly with the spacing that we have in our system. So making sure dimensions and mostly dimensions match up. I kind of ran through that and skimmed over some things, so there might be a lot of questions. Anyone got anything?
Yeah, so you said you're gonna do injection testing. Is that on the ground? I mean, obviously,
Yeah,
when you do flights, you're gonna do that, but so tell me about how you're gonna do the injection test on the ground.
So injection test, I'll work with avionics, and we'll set up a system where we have our nose cone and body tube, and I'll just put gunpowder into our injection caps and just verify that the pressure difference in the rocket will cause separation from the nose cone and the body tube. Is that what you're looking for? Or is there something a little bit more? We'll just set it up on the ground outside.
Okay.
Yeah.
All
We've
No,
done
you
this.
got it.
Yeah.
What's the plan this year? Are we still gonna try to do O-rings? Something around the bulkheads?
Yeah, we'll likely try to have some sealing method. Hopefully we'll have higher tolerances on the recovery bulkhead, so there won't be as many problems with trying to seal it. But we're still trying to develop this.
Was there incursion, residue and stuff? Yeah, again, I didn't look at it after the flight. Is there incursion into the electronics section of black
I
powder
don't think
residue?
there was. I think
There was. At the ejection test, yeah.
No, I mean after that.
Oh, no.
Or even after the test? That's what I was just wondering, because that's the difference in this much volume to pressurize versus this much volume to pressurize.
We did change it a lot towards the end of the year. I think we got something that works fairly well, but it was not.
So we go back to your plan for the year?
Oh, yeah.
So you have performed the drop test before fabricating the parachute. So what would you be using during the drop
Yeah,
test?
so we still have a lot of parachutes that are just in the, I guess, in our cabinet. So I could just dig through there and find an adequate parachute to use for the drop test. This is just so I don't want to try to rush anything. I really want to work on the system and not have to worry about making the parachute before the drop test, because I want to do the drop test, then we have our test flight. And so I just want to make sure that I have enough time to work on everything. And I know that most of those parachutes are fairly reliable. Or no, they're reliable. So I'm not too worried about that. Yes.
If the whole point of the drop test to test parachute tangling and such, then is it still going to be a high fidelity test if you're not using your actual parachute design?
I would honestly say the point of the drop test is to make sure that the system of releasing the parachute works, because I don't think there'll be too much difference in like parachute A versus parachute B when releasing from the bag. Okay.
So do you plan to have the parachute fabricated before the test launch then?
The range is kind of in between when the test is, so that's a possibility. I'd like that, but we'll see what happens. I want it to happen, but I obviously like extended a little bit past there, so it's kind of how long does it take me to build a parachute? I don't know. Yeah.
Is the parachute design gonna be similar to last year's, or are you planning on changing it at all? Or is like
It's
what we
probably
planned
going to be
do?
similar. I mean, I'm still gonna like look at some research. I don't know. I'll look at designs, but yeah, I doubt it will be too different. We saw that there's some questions.
Yes, there are a few questions in the chat as well. So Alan asked if you have any initial calculations of how long it takes the main to release.
I'm guessing that's once the tender descenders are charged. I have no calculations, but I'd assume a few seconds. I have to look into that more. I haven't done too many calculations, I'll say, especially with the release. Most of my calculations have just been like design based and dimensioning as of now. Yes.
And then Casey also asked, with the nose cone landing separate, will you be tracking that portion?
Yeah, we're gonna have to do that, since it wouldn't be a recovery system if we weren't able to recover all of our pieces. So I'm gonna try to work with avionics on that, seeing where we could put the tracker that would allow us to track it, because there was difficulties with carbon fiber. So we might have to make a new spot or find a spot. I am making the bag this year, so I can see if we have any options of putting the tracker in the bag.
I think we probably would be able to put the tracker just inside the nose cone, so
Okay.
the one end would be fully open.
Yeah, that would be the safer area, as long as we could do some testing with it, put it in there and see if there's any like problems.
Great. And then one final question, this one we probably want to wrap this up. But Alan said for the drop test, are the skydivers allowing you to use their equipment, or are you making custom gear?
So talks with the skydiving instructor have been pretty short right now, because one, I still need to work on the system, and two, there was not really too many times that he would be able to help me early on in the year. He said later, so I have contact with him. I have his number, but I don't think. I am a little confused by the question. Their equipment, I believe we're just going to get in the plane and throw it out. That's what I assumed, but he hasn't given me too many details of how it's going to actually work. But he said that he has done it before and he could help me.
Thank you. That's all the questions.
All right. Now moving on to payload. Adam.
Hi there, I'm Adam. It's no pleasantries, let's get on to business. So the purpose of this project is to design and manufacture a payload bay in the 3U CubeSat structure. So the CubeSat structure is just it's like a universal form factor. I believe it's 10 centimeters by 10 centimeters by 10 centimeters tall per use 10 by 10, 30 centimeters tall. We're going to generate electricity using the motor's energy. We're going to use the generated electricity to power a payload. The payload is the thing we're powering is kind of secondary to the power generation. We're to generate electricity. And we're doing an outreach with Metro High School for them. They're doing a payload competition design project. We're going to incorporate that payload. We will do that. For this payload is that it has to be self-contained. I don't want to have to make a recovery system for the payload, and I don't want it to interact with other things. You can alter the flight path. That's just an ESRA rule. Most of the 3U form factor CubeSat. We get bonus points for that, and it has to weigh 8.8 pounds. That's also a competition rule. So the idea behind the electricity generation is Faraday's law. Basically, if you pass a magnet through a coil, it generates a voltage called back EMF. That's how a generator works. If you drop a magnet through a copper tube, you can see that in action. The magnet will slow down. And the magnitude of that voltage that it generates will be shown by equation 1 there. Is the strength of the magnetic field times the width of the magnet times the velocity of the magnet. So basically, to generate more voltage, we're going to be focusing on optimizing the velocity. Next, it's going to go, so that voltage represented here in the schematic is going to go through this circuit, which goes through transformer to amplify the signal. This will make it into, and this will generate an AC voltage because it's oscillating in nature. This will make it a DC volt current. And we're going to store it up in some capacitors until we get to a certain voltage. And the Zener diode will basically prevent the current from flowing until a certain voltage is reached. And the camera, we'll get there in a second, runs on about 3.3 volts. That's kind of what we're looking at now. So 3.3 voltage is reached. Zener diode opens. This inductor is supposed to extend that current to the duration. I was talking to Peter a little bit. Inductor might not extend that current duration. I'm not an ECE guy. We'll do some testing on that. Mention power. Signal modulation. We need that circuit because we're not expecting a very high voltage. We haven't run the exact calculations yet, but the oscillation should be quite small. And for the camera, the payload idea we're going to do with the electricity is to power a camera. We're going to log that data as far as we know. Since the power generation will be intermittent, it's not going to be a constant power. I'm thinking we're going to have the camera powered by an Arduino, but only have it fire when a signal from this system is sent, and that'll make it take a picture. Quick system overview. Payload bay is made out of a CubeSat form factor. Its assembly is made out of basically 2 parts, 5 base plates and struts. Struts just square bar base plates, just bad plates to hold it together. And the actual payload is a camera that is powered by a signal modulation circuit, which is powered by a magnetic coil rig, and which is mounted on a bunch of springs. 2 springs. And risk matrix, I'm not a fan of mixed risk matrices, so I'll just talk about the risks. The main thing to worry about is magnetic noise from the payload and interference to the avionics bay. So to prevent a magnetic noise from the payload structure from the CubeSat, we're going to make it out of a non-ferrous steel. We could also do aluminum, but it's really kind of difficult for that 8.8 pound mark, so we're going to do steel. I believe I chose 3 or 4 stainless steel, which is not magnetic unless it's cold worked. We got hot worked, so that should be fine. In interference with the avionics, I'm going to put the magnets system on the furthest U away from the avionics. So I'm not expecting any interference because if I remember correctly, the magnetic field drops off to the square distance. So we'll do some testing. And for the year, so for the rest of the semester, we're building this CubeSat payload bay, testing the payload concept, taking the system design. I just ordered the materials for the CubeSat a couple days ago, so that should be in weeks. Start out a machine shop for that. Testing the payload concept. We're going to make a test rig. It's spring, magnet, coil around it, hooked onto a fastened rig. We're going to have a voltmeter there. And we're going to oscillate the magnet and see how many volts it generates. And then starting next semester, we'll build this circuit and code it. And not really sure how long that's going to take. Nobody is in the payload team is an ECE or CSE. I think we can try this one. We'll see. And based on these tests, concept tests, and our circuit, we should be able to get enough parameters to decide what size magnet we want to balance out strength magnetic field velocity. And then after that, we're going to assemble the payload, test it as a full kit, and then I don't have very many details on Metro's payload yet, so I just put it at the very end. We're going to incorporate it. It'll probably be before the end. Any questions?
Yeah, so what you're assuming, or are you relying on the acceleration of the rocket to oscillate the magnet?
Yes.
Okay. So you get a couple cycles, 2 to 5 cycles per flight.
Yes. I'm only expecting, I didn't include it on here. I didn't, but I came up with a graph. It was basically the opposite of the thrust curve from the motor, because it should be motor compresses the springs, force lets off the motor, magnet comes back, starts oscillating, short time, EMF done. So I'm expecting maybe 4 to 5 pictures from the camera. That'd be nice if we could get more. If we got more than that, would probably be coming up with a better circuit. But we were kind of limited by the experience on our team. We're all mechanical aerospace guys on the payload team.
Has Metro narrowed down for a payload, or?
We're still working with Metro. We kind of have a 6-week run with them. I believe they'll be presenting their proof of concepts and working on something. So now we're still deciding. I think there's about 6 potential ones right now.
We're on a 6 weeks into the design competition with them.
So it's going to be the last week is when you decide, or they decide.
We should have a pretty good idea following the presentations, which will be next week.
Try to pick it back up.
I just had a quick question. Are you planning on creating a Simulink model or something to get voltage estimates, because it's just like a dynamic system?
I don't know how to use Simulink, but I do know how to do Laplace transformations in MATLAB. So I got the equations of motion set up.
Right.
I didn't include them, but it's basically your standard MX double dot plus
Right.
CX dot plus 2K
Oh, I see, I see.
X equals force of the rocket minus the mechanical force of the magnet. I can get an analytical solution off of that. I just need to get measurements for the damping coefficient.
Okay.
Or can I can assume no damping because I don't really care about train force.
Yeah.
I think. Corey, do you know Simulink?
Yeah, I've been working on the Simulink model.
There you go. He can do the Simulink.
Hey, sold.
So yeah, we're planning on doing that.
That's fantastic.
We do have a couple questions in the chat as well. Casey asked if higher flight data can inform these estimates, and he's referring to when you were talking about the oscillations at launch.
Kirsten Kirby sent me a message on Slack asking about the Good Vibes project a few years ago. I don't know where the data for that is. I believe they measured vibration of the rocket. If I could find that data, I would be able to get some good estimates of what kind of voltage will generate. Besides that, I'm going to basically rely on the threshold motor calculations.
And then one last question: are there any concerns with moving mass affecting flight stability?
The magnet's it's 1 inch tall, 1 inch diameter. It's so small. Even if we had 10 of them, I don't think that's with it.
And that's all from the chat.
All right, so we're gonna wrap up here. That is everything we have. So we'll open up one more time to questions for any of the other subsystems that we went over. But other than that, we'll be closing things out. So if there are any other questions, feel free.
I've got one for aerodynamics and structures. I know I assume you guys are communicating on your schedules here, but to me it looked like aerodynamics was supposed to be working on the nose cone design while structures was supposed to be building the mold. So how does that work?
At least, like, I think we're planning on doing the same shape.
I know you were looking. We're in the middle of testing a different design right now.
Because
I can comment on that. So the whole process of building the transition and nose cone molds takes a good while. So there should be ample time for them to finish their nose cone analysis. And in that time, we can work on the transition, work on the other parts. When we finally need the finalized shape is kind of the last step of making the plug for the molds. So that's something that we can push off to the end of the
Just something I noticed.
Yeah, don't write your schedules, just as the last thing. Make sure your schedule's jive.
Oh, yeah.
Good catch.
Thank you.
Nothing in the chat right now. You can add a couple minutes.
All right. Well, then with that, we'll wrap this up here. So thank you again for everyone for joining and giving us feedback. We really appreciate it. It's really kind of how we know that we're doing good things here. Thank you.
I had a question about the avionics.
Yeah.
You gotta run that.
So